a lot of the ideas in chapter 4. There's some, because what we're going to go to, what we're going to wrap chapter 4 up with here, some theorems about derivatives and calculus and so forth. So they'll be based on some of that. So it won't be a lot of calculating, but it'll be a lot of short answer, some true false, some stating theorems, some of those kind of things. And you'll see as we get into that this week. So that'll be somewhere around next Tuesday, probably. So I have this take-home thing that we'll be doing, and you'll be working on. We'll have this quiz about next Tuesday, and then probably it looks like the first midterm maybe will be next Friday, so a week from this Friday, and then the other one on Monday after. So, and one is calculator, one's no calculator, and each one is some multiple choice and some free response. Okay, so we haven't had many grades right now, and then we'll have a bunch of them right kind of in a row here. Remember, the midterms are scaled, but even with that, I mean, to do well, you need to put time in on this, okay, and ask questions. And the answers to these sample ones are in this book right here, and then our last two packets will be from an older set of practice tests that I have. So anyway, so a lot of ongoing stuff. We'll be having some short assignments in the book probably on some of the days, but then a lot, and then also time to be working in whatever our current packet is that we have. Okay? All right. So with that said, what questions did you have here that you'd like to look at? Because we'll take some time on a number of days to talk about some of these problems. Yes?
Number 35.
35. When we hand these in, what I will do is they'll be worth about 7 points each. There'll be 4 of them, so that'll go in as about like a 28-point grade, so about like a quiz grade. Okay? Be partially on effort. And so, like I was telling you, I know I already told you this, that even though these are multiple choice, and on the actual test, the multiple choice will just be right or wrong, on a scan sheet probably. But on these review packets, I want you to show work where it's necessary, okay? And I know the problems that there's no way you did, even if it's a calculator section, like this one's in a calculator section, even if it's one where maybe you just got on your calculator and did stuff. I want you writing down stuff just like you would in a free response question, okay? Because that's the purpose of this, is to review and to practice, and partially you're doing this for a grade, so I want you to show that work. Now, there are clearly some problems where you don't need to show any work, and I understand which ones those are as I go through, okay? I'm also going to pick out some, a handful in each packet that I will look at more closely, okay? Typically, I pick ones where I know what kind of work should be written down and so forth, okay? All right. So anyway, is this the one right here, Down?
Yeah.
Okay. So this shows a road, it's a parabola, it's a line first, it's a parabola first until point B. They tell you that point B is basically the point 1,000, 100 right here. It's 1,000 feet horizontally from A, and it's 100 feet higher. So we basically know point B is that. Since the road is smooth, R prime is continuous. So that's one of the things that we're going to talk about, this idea of differentiability, smoothness, one of the theorems we're going to be running into later on. And then they want to know what is the value of B. And so when you have this, basically the key is this right here. R prime is continuous. That means the derivative at this point, the derivative of the parabola has to equal the derivative of the line. That's basically what they're saying. And so, and we know the line and the parabola both contain this point. Okay? So we know that when we put a 1,000 in for X, we're going to get out 100, okay, on the parabola. So that allows us to find point A, or what A is, okay? So we get A equals 100 over, and 1,000 squared, that'd be 6 zeros. Divide, so you have 2. So A is equal to 1/10,000th. So that allows us to get that. And then also we know the line contains that point. So if I put in a 1,000 here, 1,000B plus C is going to equal 100. Now I'm not sure I even need that, to be honest with you, because again, back to this, the key is we know R prime is continuous, so we know the slope here is the same as the slope going forward. Well, the slope of the line is what? What's the slope of the line? What would it be? B, right? The slope of the line is B. Okay? So we don't know for sure because we got two unknowns right here. But we know what A is. We know the slope of the line is B, and we know the slope of the parabola is 2AX, right? That's the slope of the parabola. Okay? Because the slope of the line is the slope all the time. Okay? Well, 2AX, well, we know what A is. We already found what A was. So that's 2 over 10,000. Okay, if I put the 1 over 10,000 in for A, and then I put what in for X, because I want to know the slope right at this point, 1,000. So I know the slope of the parabola is 2AX by just doing the derivative. I found out already that A is 1 over 10,000, and so now those 3 zeros, cancel those 3 zeros, I get 2/10 or 0.2. So the slope there is 0.2. Now what they want, the value of B? Yeah. And so that's got to be 0.2. Okay? Because the slope of the line is B and the slope of the parabola, and that actually something we're going to learn in section 4.9, differentiable. To be differentiable, we have talked about it with piecewise function. We've said for a function to be continuous, they have to have the same y value, but you could have one graph do this and then the line take off like this. Well, it's continuous because you don't have to lift your pencil. There's not a break there, so that's continuous, but it's not differentiable because the derivatives aren't the same. It's not smooth. It has a sharp point. But if a graph is smooth, that means that not only do they share the same point when it's switched, they share the same slope. And that's what makes it smooth. So their derivatives have to be equal. So that was the key. Okay? All right, what else? What else? 43. Oh, this is a good one. You know, you never know on the multiple choice. Sometimes you get one that's just, you do about one thing and it's just there. You know, you don't have much to do. Look at a graph, whatever, and then you get into one that takes a little more time. Now, this is a calculator one, but again, remember, the directions of the calculator problem simply say that a calculator may be necessary for some problem. Okay? There are some where it probably doesn't help you a whole lot, so don't be fumbling around with your calculator trying to do something that you're not used to doing and you're not sure what to do just because you think you're supposed to use your calculator. And how many points on this curve will the line tangent to the curve pass through the origins? This is a little bit of Shanghai. So let's say you had a thing like this. Okay, I don't know, who knows what this looks like. But here could be a point right here. Right? This is what they're talking about. So here could be a place where the tangent line would pass through the origin. And, well, I don't know, I don't see, maybe this, it's that wouldn't be that much, I guess, but, something like this. So maybe here's another tangent line that passes through the origin or something like that. Okay, but the bottom, so in a sense it's a Shanghai because you have a tangent line and we don't know where it's touching the curve, but we know another point on there, right? That's the essence of Shanghai, right? The essence of Shanghai is you have a tangent line on a curve, you don't know where it's touching the curve, but you know another point on the line. And the other point is the point 0, 0. Okay, so call this XY, call this 0, 0. Right? So really the key to this one is just identifying that you have a Shanghai situation. Okay, so how do we solve the Shanghai situation? Slope in two ways. One of them is slope between 2 points. The other is derivative. The other is derivative. So, the derivative here, y prime, would be 20x to the fourth minus 12x to the third plus 30x. That's the derivative. That's the slope of any tangent line on that curve. That's what derivative is, the slope of the tangent line. Right? By definition, slope at a point, and by slope at a point, we mean the slope of the tangent line at that point. So that's one way to write the slope. And the other way to write the slope of a tangent line here is slope between these 2 points. So y minus 0 over x minus 0. Right? Just do the slope between those 2 points. Now what can we put in place of y? This equation right here. So what I've got is 4x to the fifth minus 3x to the fourth plus 15x squared plus 6 all over x. That's got to equal the derivative 20x to the fourth minus 12x to the third plus 30x if I didn't make a mistake there somewhere. And now you do a solve on your calculator. Go ahead and plug that in. Let's go ahead and do it. So do a solve on your calculator right now. You could multiply that x over there and you could rearrange some things, but I might as well just type it in just like that. Okay? So while you're doing now, just reiterate. It's a recognition that this is the Shanghai problem is the key to this. At how many points on the curve? In other words, they're saying find x. Find where the tangent line is touching the curve that meets these conditions. That's what the Shanghai problem is. 2 ways to do slope is how you solve it. One is slope between 2 points. So you got your unknown point, xy, where it's touching the curve. You got this other point where it's touching, because that's almost always what you have in Shanghai. You don't have where it's touching the curve, you have another point that it goes through. So slope between those 2 points, and then derivative. Derivative of the curve is the other way to get slope. What do you get? And actually, all you need to know is how many, right? You get 1. Okay. Yeah, this says A1. Roughly point, it says on here 0.6. 0.6 something. Okay.
You can also like do without Shanghai, like if you did, what I did was like y equals y prime x, and then if you like solve for that, like that's one was, isn't that one?
Yeah, I mean that'd be the same thing. I mean, well, yeah. What? I guess I'm not
Like if you,
seeing how that's different, because basically I set up this.
okay.
That's what I set up. This equals that. So, yeah. But you're saying because it goes through 0, 0.
Yeah. So like if you like do y equals everything, that's solve for that.
Right. So y prime is your slope. The slope of that line, y equals, in this particular case, because it's 0, 0. Especially, but that would work anytime. Right. But that, again, no matter what this point here is, so let's say this is, so let's say it goes, let's say this point isn't 0, 0. It's just AB. It's some point AB. So this would be y minus b. This would be x minus a. And so what you'd have is, it'd just be your point slope form. You're right. Y equals y prime x minus a plus b. Right? Does everybody understand what Harish is saying? It's essentially the same thing. So essentially Shanghai is going to be slope between 2 points. One of the points will be xy, one will be some other point, call it AB. Okay, this will be your slope. Over here's the slope of the thing. So if I wanted to, I could multiply the x minus a over here, add the b, and isn't that just our point slope form, right, of our tangent line, where the slope is what? The slope is the derivative of the function. Your other point is this, your other point is that. Right. So if you wanted to remember that would work too. Yeah, that would work too. Set a tangent line equation where you take the other point you know and the derivative and put it in there. Yeah. Same thing. Same thing. Okay? All right. What else? What else? What else? Which one? Yes. Moving on down. 44. Population grows according to this equation. population will approach a limiting value as time goes on, during which year will the population reach half its limiting value. So again, now, since you do have calculators, you could just graph this thing. Okay? You could just graph this thing. Now, it probably takes more time to graph it. It's an e raised to a negative power. It's going to be one of these kind of situations. So that's its limiting value. But really, I think what they wanted you to think of that as kind of a limit problem, literally. As t gets really, really big, what happens to this? Doesn't that get really small, right? Because you have e to the negative infinity, like having 1 over e to the infinity. This is going to get really, really small. It's going to go towards 0, which is going to wipe out this part, which is 6,000. So the idea was that you would just look at that and see right away that the limiting value is going to be 6,000. I mean, it's just this graph shifted up 6,000. Okay? So when will it reach half of this? Well, when will it reach 3,000? So all you have to do is put that in your calculator. So, right there. Just put that in your calculator. So the calculus part of this is that limit idea, that the limiting value, but again, you could have graphed it and just saw it probably traced that it's going down to 6,000 as well. Okay? And then according to the book here, it comes out to about 3.8, which would be what year then? Fourth year. Because if you get 3.8, that means, right, if you're 3.8 years old, what year of life are you in? You're in your fourth, right? When you turn 3, you've lived 3 full years, right? When you turn 3, you've lived 3 full years. So when you're 3.5, you're in your 4th year. So 3.8 is what you get. The correct answer would be 4th. Okay, what else? Let f be the function given by tangent x, let g be the function given by x squared. At what value of x do the graphs have parallel tangent lines in the interval 0 to pi? Okay. Now, it's not a bad idea to know what tangent looks like. You know that the tangent graph, at pi halves, negative pi halves, it kind of comes through and does this. And it says from 0 to pi. So pi would be right here when it comes up and kind of does one of these. So we're looking at really just from here to here. Okay. But parallel tangent lines means what? Their slopes are the same, which means their derivatives are the same, right? So the derivative of tangent is secant squared, and the derivative of x squared is 2x. To put that in your calculator, that's 1 over cosine squared, so maybe multiply that over to the other side. So multiply a cosine squared to both sides and get 2x times cosine squared. Now remember to put that in your calculator. Put it in like that, right? So solve an equation like that. Now remember, whenever you do a solve on one of these, now it might not matter on this one. It might not matter on this one. Now, first of all, you'd have to put a time sign between that x and that parenthesis. Make sure you do that. And then this is where you could do that vertical bar on the outside. So you do your solve, comma x, vertical bar, and this supposedly 2.083. Okay. Again, this is really about the midterm and the final, really about just getting comfortable with these problems. So it's over time. That's why it's so important you put in the time. That they're going to be hard at first. And then over time, you start seeing some of the same types of things. You start recognizing it. And the value in it is I think what I've learned over time is it really cements just the concepts that we've been learning, because so many of the problems put several concepts together in one question, and so it really helps us with that. So that's why we do it, really. Okay, not just to give you a really hard test, it's just to help you do that, and that's why I scale. All right, let's keep going. We got a little more time. Maybe we'll do them all. Wasn't there a Shanghai in the tower one? Number 4. Right? I mean, maybe I won't go all the way through it with you, but just, here you got the same thing. You don't know where that's touching. And this tower is 16 feet high. So what would this y-intercept of the graph be? 100. So we know that this is the point 0, 1, 16, right? So again, it's that same scenario, right? And so Reese, you can set it up the way you did, So it's just y minus 116, x minus 0, and then do your derivative of that, the y prime on this side, and solve it. And then once you find that point, then you can find, then you do have to do a little more. Then you've got the equation of this line, right? So once you find that point, now you can get your slope. You can get the slope of that line, because you got 2 different ways to write slope right here. So once you find that point, you can find the slope of that line. You can write the equation of that line, and then you've got to find this point here. Okay? So take the equation of that line, put a 0 in for y, find the x, and that's, you can find that distance once you know this point, because you can figure out this point too from the graph, right? So you can figure out this point. I think, is it 200? I think maybe this point is 200 right here. And so you can find this point, then you can find that distance. So you can get all of those different things from the information that's there. So just, that helps you get going. But again, Shanghai situation. So every time you see that, you know what to do. All right? Anything else? Anything else? Anything else?
Could you do 1B?
Find the range of f, use f prime. So here's a common thing they do on the AP test is they'll give you a function and they'll go ahead and give you the derivative, because they want you to use the derivative, which is what they're asking you to do in part B, and they're afraid that you'll mess up the derivative, and then obviously you won't be able to go any farther if you don't have the right derivative. So they just go ahead and give it to you, which was nothing but a quotient rule. So it says find the range of f, use f prime to justify your answer. Well, first of all, let's draw the graph, because that's going to be helpful, which you had to do there. So so it looks like it's got a vertical asymptote at -3 right here. And then it comes down like so at about what point? That's what we don't know, right? And so the reason the derivative is going to be useful, and of course you can do a, that's a bad example, but there actually is an asymptote that goes right through here. There's a slant asymptote that goes right through here. But so the range looks like, so why are they saying use f prime? Because the range is the outputs, right? So it looks like if you have this graph, now again, you could trace on your calculators, right? Is this a calculator problem, I assume, or it's not? It is.
It is.
It is, right? So you guys on yours, you could just trace. But it's going to be negative infinity, the range, right, is negative infinity to where? Well, whatever the top of this hump is, we call it a local max. And then, so the range is going to be from negative infinity to there, and then from there up. In other words, it's the local max and mins that we need to know. They want you to use F prime to get them, right? Instead, just trace on your calculator and show and see what that point is and see what that point is, right? They want you to understand, oh, you need to know the local max. Well, that's when the derivative is 0. So the derivative is a fraction. It's going to be 0 when the top is 0, because we know when the bottom is 0 is this vertical asymptote. So we factor that. I assume, does this factors nicely. So when x equals -2 and -4, so then we plug those back in, f of -2 and f of -4, to get what those values are. This would be the one at -4, so we plug in -2, we have 4 minus 8, that's -4, -2 plus 3 is 1, so that's -4, so that's that one right there. Is at -4. Then we put -4 in there. 16 minus 8 is 8. -4 plus 3 is -1. So that's -8. So this point right here is -8. There we go. So it's this work they want to see. They want to see that you do the derivative, set equal to 0, that you're finding these local max and min points. And so then now your range is -infinity to -8. And then -4 to infinity. Okay? All right. What about, we haven't done one of these for a while, but we're sitting here, we're just looking at this problem. And it says, find the limit of f prime as x goes to positive and negative infinity. Okay? Okay. So as x gets really, really big, what matters in that f prime? The high power. So on the top it'd be x squared, on the bottom it'd be x squared, so the answer 1. What about negative infinity? Same thing, because they're squared, right? They're squared, so it doesn't matter if they're negative. They're 1. Now that's f prime. F prime is a slope. So what's that tell you about when this graph was taken off? When this graph was coming down here and going like so, and it was coming up here and going like so. What's that tell you about this? Slope's approaching 1. The slope is approaching 1. So it's a curve. It's a curve. It's getting closer and closer to that asymptote. That asymptote must have a slope of 1. That asymptote would have a slope of 1, and the curve is getting closer and closer. Okay? And I don't know, maybe they even said, yeah, okay. Yeah, I thought that'd be a great question. That's why I didn't even read D, but explain what your answer to C tells. Right? And that's what it does, right? And they like to do that. They like to give you a question, you know, where you have to do like they're just a limit problem. But then what's that mean? What's that mean? Okay, and that's stuff we haven't always done a lot of, and that's what I like about this stuff. It helps bring it together. Okay. One more. One more if you got one. This is probably the last chance time we'll talk about sample 1, so as a group. Anyway. But we've done quite a few of them already. That's 45. And we do get to spend a little more time on this one, probably as a group, than we will on some of the others too. 45. Okay. Now this one I would say to you will be a lot easier later in the year. Okay. This would be one where we would actually do areas on this. You know, remember we talked about areas a little bit way at the beginning of class, and that's how we would probably talk about this one. But it says, let f be differentiable. The graph of f prime is shown. F of 2 is 10. Which of the following best approximates the max value of f? Okay, well, from 0 well, let's see, f of 2 they said is 10. Okay, so from 2 all the way to 6, f prime is what? That's important here. Positive. So what's f doing? Increasing that whole time. So the max has to be where? At 6, right? So the f graph we know is increasing all the time. Now how much is it increasing by? Well, again, we will use areas later on, but we can do it with slope. Okay, we can do it with slope. So in other words, right here at 2, so if I was going to draw an f graph, basically this would be like trying to do a little better version of what we used to do when we would draw an f graph from an f prime graph. So if f of 2 is going to start at 10, okay, so they told us f of 2 is 10, and right here the slope's about 16. Now let's just say from 2 to 3, it goes from 16 up to 28. So what's the average of that? Between 16 and 28? About 22, right? So it went over 1, and let's say it averaged about 22. So when it went over to 3, it went up 22. So now we're at what, 32? You see my rationale for that? Okay? Now, go over another one. It went from 28 up to, I don't know, 32. So it averaged about 30 or so. So when we go over another one, it's going to go up another 30. So now we're at 62. And then from 4 to 5, it went from a 32 down to a 25. So let's call that, I don't know, 28, maybe 29. So it's going to almost 30. So we'll say it goes up to about 91. And then from 5 to 6, it's at 25, goes all the way down to 0. So let's say that's 12 and averages about a slope of 12, right? Because I'm going over runs of 1. So you go over 12, that's about 103, something like that. Now, you look at that. Now, here's their answer. And maybe did I give you these already? Did I give you guys these answers? Yeah, choice E, 1/10. I had about 103. And that seems to be the closest. Now, you might be saying, boy, that's pretty approximate, for that to be right on that. But with areas, we could probably maybe feel a little more comfortable. But that's not bad. That's not bad. Okay, so that would be the idea of that. Okay, let's we'll put that aside, and again finish up whatever you don't have. But they will come a little more fast and furious because we will be doing some other work along the way too. So probably what you want to do is I'm trying to make the homework assignments be such that they're not terribly long. I mean, if there's one night that it's a little longer, then maybe that's it. But the idea is that you would be doing the homework assignment and some packet work, right? Homework assignment, a little bit of packet work. And just so you're not trying to rush at the end just to get them done, to get them handed in for points, because that's fine to get those points, but it's probably not helping you get ready for the midterm. Okay. All right. So we're gonna talk about something here. We're just gonna do a little bit of this. This could be on our no calculator quiz. Could be on that take home. This thing called Newton's method. On the no calculator quiz, you won't have to do any of these calculations that we're going to be doing on this, but be able to describe the process, what it is. Now, what Newton's method is a method for finding the zeros of a function. Now, you think about calculus, that's a pretty important deal. Now, this is something I never learned in high school, calculus, okay? Or even, I don't even remember talking about college calculus, to be honest with you. And the reason it's kind of come back is because of technology, because of our calculators. Because the calculations would have been so ridiculous when I was in high school that, I mean, for a TI-30 calculator to do, would have just taken enough time that it wasn't, probably teacher it wasn't worth it. I don't even think it was in textbooks. But it's been around a long, long time. But it was only worth doing if you really, really needed this information. But think about how important finding zeros of a function is, right? Do the derivative, set equals 0. Selection points, do the second derivative, set equals 0. Yeah.
What type of calculators did you use in high school and college?
I'm just young enough. I missed out on the whole slide rule era. You know, you ever see Apollo 13 and you see the guys? And that would have been the early 70s. And so when I was in elementary school in the early 70s, and we didn't use calculators. And so when I got to high school, the TI, the one I remember, the TI 30, and you probably, I should pull up a picture. That's a great question. Yeah, that would be something like it with the old LED, the red readouts. So that was, and they came in a carrying case and kind of this denim kind of zip up carrying case. Yeah, that's pretty typical. So I was able, when I took like trig and stuff like that, we had this, but we still did. I mean, it was new enough. And you could get them for about $40 then. I mean, and I remember our teacher always telling us stories about how 5 years ago they were 95 or 100, and so a lot of students didn't buy them. But, geez, you guys bought one, that was a lot of money back then. So, but we still did like trig values. So all the books still had tables in it. And you looked at, so you wanted to find the sine of 43 degrees, you had to go to the back of the book, look up 43 degrees to the sine column and get a decimal, and you write that down, and same with square roots, you went to the square root of 7, you went to the back of the book, there was a square root table, you looked it up and you got the decimal and stuff like that. So, back in the day, I used to talk about this in my computer class, a calculator or a computer, that term at one point in time in history would refer to a person, not a thing, not a machine. It was somebody who made these tables or found errors in tables and, did the calculations for these tables. Now, how did they do it, right? Like sine of 43. How'd you do sine of 43 if you didn't have a calculator? What calculations did you do? Well, that's actually something you learn in Calc 2. They're called Taylor polynomials, or you take polynomials and fit them to different curves, like sine curves and stuff. And then nice thing about polynomials are just multiplication. I mean, even if it's x to the 5th, you just take a number and times it by itself 5 times, right? So you can take it, you can solve polynomials. As a matter of fact, that's one of the things, that's where this Newton's method is going, actually, is how you can do some simple calculations. When we say simple, we mean add, subtract, multiply, divide kind of calculations that you could do back in the day before machine. Okay? So we did more by hand than you guys do, but not a lot. We did get it. I came at a time where I did get to use my calculator for some things. So how do we find the zeros of this thing? There is no quadratic formula because it's a cubic. So how do we do it? Now you guys did this in honors algebra too. Do you remember synthetic division? A little bit? Kinda, sorta, okay? Rational root there. We don't do it in pre-calc anymore. We used to do it a lot, but because of calculus, stuff like that, it's kind of like, well, it's interesting and good to do, but it's how applicable is it? Because people just don't do it as much anymore because the technology does it. And so let's just talk about what do we mean. So basically we're saying, where does this graph cross the x-axis? Right? Where does this cross the x-axis? Where does this equal 0? Well, one way to do it is guess and check, right? So we start plugging in some numbers. So we plug in a 1. 1 plus 1 plus 3 is 5, right? And then we plug in a 0. What do we get? 3. And then we plug in a negative 1. Negative 1 plus negative 1 is negative 2 plus 3, and that's 1, right? And then we plug in a negative 2. Negative 8 plus negative 2 is negative 6 plus 3. Did I do that right? Negative 3. Now, we didn't find one. We were hoping to get a 0. But what did we just figure out? There's got to be one in there, right? Now, the reason we know there's got to be one in there is because we know this is something we're going to study in Chapter 4 as well, is continuous functions. We know polynomials are continuous. We know it just didn't jump from 1 down to -3. We know it had to cross the x-axis. That's something actually we're going to study called the intermediate value theorem. It had to hit all of these values between 1 and -3, so it had to hit 0. So we know there's 1 in there somewhere. And then we could just keep guessing and checking. We could say, well, let's try -1.5 and let's plug it in. That's not a lot of fun. But if you lived 100 years ago, you were just used to doing that. You did this by hand, right? So all you had to do is -1.5 times it by itself 3 times, times it by itself twice, I guess, and then, find that number. And you can get as close as you wanted to, depending how desperately you needed to find that number. Okay? So guess and check. Synthetic division allowed you to do that a little quicker. Synthetic division allowed you to plug numbers in and get those answers a little quicker, and so that's where I came from. All right. So we know there's somewhere between -1 and -2. Here's what Newton's method is about. Now, I don't know that this is really discovered by Newton. I think it's more named after Newton as kind of an inventor of calculus because it uses calculus, okay? So here we got a function, crosses the x-axis. We want to know where that is. So we've just showed how we can plot some points. We can kind of figure out maybe and get close to where it crosses, okay? We're going to call that our initial guess, okay? So we're going to guess that the root is that. We're picking a number. Again, pretend we don't know what the graph looks like, right? I mean, I don't know what x cubed plus x plus 3 looks like for sure. So pretend we don't have it, okay? So we're making a guess. And we plug that in to see if we're right. We're hoping to get what? 0 when we plug it in. We're hoping to get 0. We did. So here's where we decide to use some calculus. We say, you know what? We didn't get 0. But let's make a tangent line at that point. Now, all we need is a derivative, and that's easy to do. We could do the shortcuts for derivative 100 years ago, right? We can do the derivative, plug that number in, get the slope, do a point slope form. Linear equations are easy to work with because they only involve multiplication, addition, subtraction, right? So linear equations are easy to work with. So let's do the tangent line at that point. And let's see where it crosses the x-axis, because think about it. We don't like solving, we don't have a way to solve this, but we always have a way to solve that, right? We can always solve a linear equation. So you take a linear equation and see where it crosses the x-axis. All you got to do is set it equal to 0. And we're going to let that be our next guess. Oops. Okay? And then we're going to try again. Now, what's the rationale? The rationale is when we get close, remember, local linearity, a tangent line is a pretty good approximation of the actual curve right around the point of tangency. So the line and the curve are pretty close to each other up here. Now here they get kind of farther apart. But you know what? It's closer than that one was. So if we repeat the process, if we say, okay, let's plug that number in, let's see if we get 0. Oh, shoot, we didn't. Let's do a tangent line through that point. And let's see where that crosses. And now let's plug that in and see if we got it. See if it gives us a 0. Oh, shoot, it didn't. But you know what? Chances are it's getting better. It's closer. And look what happens. The closer this gets to the x-axis, the closer our tangent line and our curve are going to mirror each other. And pretty soon, that tangent line is going to cross the x-axis pretty much at the same place this does. And we just keep repeating that and get as close as we want. And all it really involves is plugging a number into a function, which we can easily do because it's cubed or fourth or whatever, and we can get that value, and solving a linear equation, which we can easily do. Okay? So that's it. That's the idea of Newton's method. I sometimes call it riding the tangent line. Make a guess, go up to the curve, see if you got 0. If you don't, ride the tangent line back down to the x-axis, check that. If it's not 0, ride the tangent line back down to the x-axis and repeat. Okay? All right. So I don't want to take the time today to go through all of the mechanics of it, but basically it would be this. It would be a little bit like what Harish said. The tangent line equation would be y equals the derivative, right, times x minus our guess, let's let x sub 0 be our guess, and then plus y sub 0, and that's our tangent line. And then basically we want to set that equal to 0. We want to see where that crosses the x-axis. Now let's solve that for x. So that will be like our next guess. So if we take away the y sub 0, which was our guess, okay, so we take away y sub 0, that would give us this. If we divide by y prime, and then we add x sub 0, actually it'd be minus, we could call that x1 or whatever. That would basically be our next guess. Okay? Now y prime, we could call this y prime of x sub 0. And actually I think I'll call it f prime. But that every single time, that would be our next guess. So our first guess minus our first y divided by our first slope, right? Or your y prime. And then that would give you your next guess. And then you could just repeat that. Okay? So that essentially gives you this formula right here. So x of n plus 1, our next guess, is equal to our previous guess minus our y value of the previous guess divided by our slope at the previous guess. And all we need to do this is be able to plug into the function and be able to plug into the derivative. And that always gives us our next guess.
Do you calculate or do that after these?
I would say I don't know the answer to that for sure. But right, when we tell it to solve derivative equals 0, what's it doing? It's got an algorithm. It's something, I would say it might be a little more powerful than this, but it is something similar to that. That's what's going on. And it's one of the reasons I like talking about it. And again, that's why we didn't do it when I was in high school. We didn't mess with this because just doing it by hand. So we can use our calculators to get it to do this a little quicker. There's kind of a shortcut I'll show you today, and then tomorrow I'll show you the super duper shortcut. Some of you might figure it out on your calculator anyway. But what we're going to do, and I guess what would be the long way then, would be write it out in the table. But we can see some things. We can discover some things by doing this. So on your homework today, you got a couple I think you're going to write out like we're going to do right now. And then you got a couple where you can just kind of do kind of a shortcut on your calculator, which I'll show you here in a minute. Okay? Which reminds me I should try to open up my calculator here. Okay, so let's take this problem we were just looking at. Now, we knew we should have one somewhere between -1 and -2, right? We narrowed it down. So, let's make our first guess be -1.5. So you guys help me out with the calculator here, and I'll get you started. But I want you to make 5 columns like this, okay? So on the take-home quiz that we have, if there's a Newton's method problem, I will say, I want you to write this out with the table, and then there'll be another problem, another part of it where maybe you can do the shortcut. Let's all be specific about that, okay? But these are the entries I want because each of these entries tells us a little something about what's going on. Okay, now, you can go ahead and go to your calculator right now, and you can go, okay, probably the smart thing to do, here would be to go define f parentheses x equals x cubed, was it plus x? Plus x plus 3. Now we're also going to need the derivative, right? So let's call that g. So let's define g of x to equal 3x squared. What is it, plus 1? Okay, so we need both of those. So now all we have to do is do f of, and then I'm going to start leaving this to you now, and you guys can tell me what you get. Negative, whoops. So it's negative 1.5. Right, and so we got that. Is that what you're getting? Okay, all right. So let's start filling in the table while you go. Okay, so what was that? Negative 1.875. Okay, and now what's F prime, or it would be G of negative 1.5? 7 point, exactly. Now, at some point, the decimals are going to start getting ugly. You want to keep those decimals in your calculator, but you don't have to write all those decimals. Maybe write 2 or 3, and that's fine. Okay, now we want to take F divided by F prime. So on your calculator, you want to go up and grab those so you've got them, okay? Or even grab, the F notation, whatever. And so what do you get when you divide those? Okay, good enough. And then we take our X here minus that. So we take negative 1.5, subtract negative 0.242, but again, go up and grab them. And what do we get? 258. And that is our next guess. Okay? So now we want to do F of the negative 1.258 number. So you go F parentheses and then arrow up. So F parentheses, arrow up, grab that number, it'll bring it back down. What do we get there? Anybody got it? We're hoping for 0. That's pretty close, right? That's not bad. Now it's not close enough, but I mean, it tells us we're on the right track. And then we want F prime. And then we want to divide those two. And then we subtract this, subtract that. Let's go one more row. Negative 1.215. Okay? So now let's put that back into the function. And so, right, by defining it, think about even back in my high school days, I would have to take this big long decimal, I have to cube it, and then plus that decimal. So even this process would be a lot longer doing that, especially if I wanted to keep a bunch of decimal places. Those calculators could store values, and so you can go back and forth, whatever. But, I mean, this, and then we can do something to shortcut this. Okay, what's F? Negative 0.020, okay, and then F prime. One point something. Okay, and then divide those. And then over here.
I think
what
prime should actually be 5.4.
I was going to say, that was a big drop right there. That was a big drop for that F prime. So what'd you have for F prime?
5.427.
Anybody else get that? Okay, and then when we divide them here, it's negative point. 2 zeros is all, and then 1, 2, 9, and then over here. Okay, so, okay there? Anybody else, some agreement? So let's look at what the different things give us. This we're hoping to be what? 0, right? If this came out 0, it'd be done. We found it, okay? So that's a good thing right there. So we know we're getting close. And then this doesn't really tell us a lot. That just tells us the slope of that tangent line. What does this one tell us? This is really kind of important column. What's this tell us? Because what do we do with this answer? So isn't this just the difference, right? This is just the difference from our last guess to our new guess, right? So what should happen is how many zeros here starts telling you how many decimals of accuracy you have, right? So you start getting more and more zeros in here. Now, of course, it's going to, because if this is getting close to zero, and then you're dividing, you're taking a number really close to zero and dividing by another number, you're going to get something close to zero. But this is telling you your accuracy, right? And of course, you can see it right here, okay? And probably what's going to happen, we're going to continue getting more and more decimal place accuracy. So if you want two, so you keep going until you get whatever your desired accuracy is, right? And so if you would go onto your calculator here, if you would go onto your calculator, you know, and just do a solve, okay? So if we go on here and just solve, what was it, F? We just go f of x equals 0, comma, x, right, negative 1.213, you know, whatever. So the calculator's got the same thing. It's got a tolerance built in. How many decimal places accuracy does it want? And it just runs through that algorithm. It just runs through whatever it's using to be able to do that. Okay? So, anyway, so that would be what we call the long way, although historically, that's not that long, right? And with the technology we have, that's pretty good to be able to come up with that. But more powerful is the idea. The idea. That's what I want you to understand. And so on the no calculator quiz, I may ask you a question about just describing how it works. Now, there's a couple in your book, they talk about a couple of times when Newton's method may fail, okay? So one time Newton may fail is, let's say we guess that the root is right there. What's going to happen? Well, we take our guess, we plug it in. We see if it's 0. It's not. Then what do? Draw the tangent line. And we write it down to the x-axis. Well, what happens if we hit right on the peak? Not good. It's never going to cross, right? Think about our formula, right? If f prime is 0, that's not going to be good, because you'll be dividing by 0. So if you happen to make a guess, now what are the chances you're going to guess right on the peak? Probably not very good. But what would happen? Well, and what if you don't hit right on the peak, but you hit close to the peak? Well, all of a sudden, let's say you guess here, and then you get this. Well, then this tangent line shoots you way over to here. And that's your next guess. Well, what happens is eventually you'll probably still find a root, but you get a real shallow tangent line, it may shoot you that, if you did ride the tangent line down to the x-axis, it may shoot you way, way a long ways away. You may find a different root or than the one you were next to or close to, whatever. That's one bad thing that can happen, a shallow tangent line, okay? The other thing that could happen, and I think you'll get to see potentially both of these in your homework. Another thing that could happen is, let's say you guess here, and you get this tangent line and it shoots you down to here, right? And so that's your next guess right there. And then you plug that in, and you take that tangent line and it shoots you right back to there. Now what's going to happen? It's just going to repeat. You're just going to keep getting that same number back. You're just going to get that same number over and over, those same two numbers over and over again. Now, so what would happen here is you plug this in, you get a number here, like say -2, then you put -2 in, you get -1.5. Put -1.5 in, you get -2. Put -2 in, you get -1.5. You just keep getting that same number. So it might just cycle. It might just cycle back and forth, okay, and not zero in, pardon the pun, but intended. We're trying to zero in on the root. Normally, what would happen? Tangent line comes down here, then tangent line comes there. Then tangent line comes there, and eventually you go down and find that root. Okay, but those are a couple of issues that could happen with Newton's method. All right, So, I think on the assignment sheet, there is, on the 4.6, it has 3, 5, and 15. So let's talk about that real quick. So, 4.6, 3, 5, and 15. Now on 15, let's see. We're on 3. Okay, 3 is just, somebody may have already even sketched in your book a little bit. So 3 is just one you're going to answer the question. You're going to kind of look at where the tangent lines would go, and just answer the question. So 3 is simple enough. 5, A, I only want you to do 5A, and that's where I want you to do a table like we just did. Okay, so they give you a different polynomial. They give you the interval 0 to 1, and they say go to 3 decimal accuracy. So pick a number somewhere in the interval 0 to 1 as your guess, and then do a table, okay, like we just did. All right, and then 15. 15 gives you a function. You do not have to do, on 15A, on part A, just solve on your calculator. Just do a solve. I don't care about, well, I'm not going to make you do a whole bunch of the tables. But on B and C, do the table. Now it says, you kind of know what's going to happen, is what we just talked about. It says, what happens when Newton's method is used for 2 as your initial guess? So you're going to do your table. Now you're going to find something right away is going to happen, okay? So you don't have to do a long version of the table. And then C said, Newton's method behaves oddly when x sub 0 equals 1.39. How and why? And then I think you'll be able to answer. You'll understand. But it's related to the 2 things we just talked about. Okay, so on 15A, just do a solve on your calculator, get those roots. B and C, do tables. 5A, do table. Okay, and then work on sample 2. Or more of sample 1 if you're not done with it. Yeah. Nope. Nope, just 5A. Yes. What's that? Yeah, eventually all of it. So I have no number in mind for now. I would just work. It's kind of like this. You know your schedule, so you know if you got some time tonight, but you know the next couple nights are going to be rough. I would spend a lot of time on it tonight, you know, or whatever the case may be, right? But we will get. There's 2 more packets. I will probably hand one out. I will probably hand one out on Friday. And then another one middle of next week. So you know what I mean? So it'd be nice to have this packet done by Thursday or Friday. Yes.
I'm going to be gone tomorrow for a competition.